In the next series of videos, I'll show you how to create an algorithm for wall following. We'll work with this wall following robot, which is shown here, and as I'll share with you the CoppeliaSim file for this. In this case, the robot is equipped with 5 proximity sensors. They are shown in blue, red, and the fifth one is in green. In this case, the wall flowing robot uses the proximity sensors to measure the distance from a wall. So LF is the distance measured by the left front sensor, LR is the distance measured by the left rear sensors, and F is the distance measured by the front sensor. We'll be using the command called sim.read proximity sensor in order to get the distance, and I'll show you how to use that. In this case, we're interested in two distances. One is the average of the distance between the left front and left rear, and the difference between the left front and left rear. So in this scene, you can see the robot, and let me move it right to the middle of the arena. Okay, let me play the simulation. You can see that the robot is traveling at a uniform speed. Now, the way this works is there is a script which makes the robot go straight. This is the script. There are 5 functions. The first function is the init function where you initialize the code. There's an actuation function which tells you what you need to do in order to control the robot, and then the sensing function senses the different sensors. Now in this case, I have 2 joints. They are LumiBot left motor, LumiBot right motor, and those left and right motor are here. This part of the code essentially gives a handle to those 2 motors. Once I have the handle, then I can use sip.set joint target velocity L motor, left motor 1, so speed of 1, and same for the right. So this code enables it to go forward. Now we can also make it be stationary by just changing this value to 0. Now you see it doesn't move. Okay, next is the proximity sensors. So if you zoom in, you see that there are 5 sensors. These can be easily seen by perhaps clicking on this: left front, left rear, right front, right rear, and the front one, which is the screen one. If you double click this left front, you can see a series of properties of the sensor. In this particular case, let's get the volume parameter. Here, the offset is set to 0.1. So you can change this to see what happens. So you can see it's this one. So if I change off to 0, you can see that this is the distance over which the measurement would take place. In this case, I've set it to 0.1 offset. This range determines how big this line is or what is the distance the sensor can measure. So let's increase that to 0.35. And you see that line has increased relative to other lines because I increased the proximity distance. Let's keep it back to 0. You can play with the other parameters to see what they do. Now, what I'm going to do here is I'm going to create a wall, and that wall is something which the LumiBot robot will detect. So for that, I'm going to add a cuboid. In this case, the distance between the length of each of these, or the sides of the squares, are about 1 by 1. So I'm going to change them to set this x distance to be 0.9. Let me try that again. Cuboid. Okay, since the distance of, or the size of the squares is 1 by 1 meter, I'm going to change this to 0.9. That's going to be the x distance. The z distance is the vertical distance, and I'm going to change that to say 0.1. And then the y distance is this one. I'm going to change that to 0.05. This is good because you can see that the proximity sensor is actually passing through that, so it should be able to detect it. Okay, I'm going to call this wall, or rather wall 1. Let's move the wall to its left. In this particular video, wall following robot, I'm only going to deal with the left left rear, left front, and the forward sensor. You can do a similar coding with the right front and right rear. Okay. And while we're at it, let's just move this keyboard slightly closer so that the blue and the red line intersect the keyboard. Okay, now we can play this to see everything looks good. Okay, now we'll try to read the proximity sensor. For that, it's best to refer to the regular API. The regular API. This will be in the reference. Search for read proximity sensor. And then if you look at the syntax in Lua, you'll see that it is uh, this is how it is to be used. You need to pass the sensor handle, and then it'll give you result, distance, and a bunch of other things. But we're interested in the first two. Result is basically saying if it's detected or not. Detected is zero. Sorry, detected is one. Not detected is zero. Distance is the distance from the measured point. So we'll use this syntax. Let's take this and open the script. Now I've already initialized um, the handle. In fact, let me call this sensor LF, sensor LR, sensor RF, sensor RR, and sensor F. So I'll put all this code for sensing in the sensing function. So let's modify this. I don't want all these except you just want the first two. So let's change the result value to, let's call it a flag. So detect, so doesn't detect. And then let's call the distance of the left front to the left. And then we change the handle to sensor. Okay, so now let's see. We have to print. I want to print flag one to see what it is. Flag one equals flag one. Just to put a space. Distance LF, or rather, let's just call it LF equals LF. That's about it. Okay, so if this all works right, and since LF is the left front sensor, when I run this code, it should give me the distance of the LumiBot or the wall following robot from the wall. So let's run this. And then we note that that's not right. It's not giving the distance, it's saying not detected in LF equals zero. And that is because of the properties of the wall, which is it's right now not set to be measurable. Okay, so what we need to do is uh, let's go to the wall. Let's stop this. Go to double click the wall. Um, let's look at common properties. Here we want it to be detectable. We want it to be measurable. And then when the wall following, if the wall following robot collides, we want it to be collidable. So with that, let's run this again. And now you see suddenly we have this output where it's saying that flag one, which says it is the wall is detected. It's also giving the distance. So it's 0.18. Let's try to do that for the left rear sensor. This code, copy it to, let's call it LR. And then this is sensor LR. And then just copy this, paste to R. Okay, so let's play this. And you see it's printing flag one, flag two, 1, 1, and then 0.18 for the LF distance and 0.16 for the LR distance, which makes sense because LR is at the left rear sensor is closer to the wall than the front one. Okay, so we have that. Let's just continue doing using the programming the forward sensor too. Okay. Next, what we want to do is, um, as I said, we're interested in these two distances. We want to find the average of the distance between LF LR to give us a mean distance, which is going to be this, the average, and then the difference between LF and LR. Now, um, the way we would do this is obviously we will define a variable AA. Let's call it average is 0.5 LF plus R, and then we get the print ABG equals G. Okay, we also want the difference. I'll call diff equals point LF minus LR, and then we print that. Diff. Now let's play this. And then you can see it's printing the average and then the difference. Now, here are some cases. Uh, Not always would the sensor be seeing the wall. So for example, if there's a corner here and this robot moves forward, just move it. Let's move it. Okay, now the left rear is seeing the wall, uh, left forward is not. And so when you run this, you see 0.056, but 0.056 is not the distance, average distance. In fact, um, it's still the same. It was about 0.17. So we want to avoid this case where we get this erroneous reading saying that this robot is very close to the robot when it is not. So for that, what we'll do is the following. We will use these conditionals to create that case. Now, in this case, we know that the left front sensor does not detect the wall. We use that information to appropriately write the value for the average. So what we want in this case is if flag 1 equal to 0 and flag 2 equal to 1, then, so this is this case when the flag 2, which is the left rear, is detecting the wall and first one is not, then we want to change the average and we want it to be just LF. Okay? And then the diff, LF minus LR, if we put minus, so this should be LR. If you put only minus LR, then that could be erroneous. So we just use 0. We just assume that we don't have information from sensor, so we do not know the orientation of the robot. So that's will work. And now when we run this, we see that we get 0.11, which is the distance of the left rear sensor. So instead of, we can do both cases when we have uh, flag, let's say flag 1 equal to 0 and flag 2 equal to 1. So flag 1 equals 0, 1 and flag 2 equals 0. Then ABG, in this case, it should only record the flag 1 sensor, so it should be left. And if will again be 0. But we also have this case where both these sensors will detect the, the wall, which is this case. So we just copy paste that here. And then we also have a final case when none of this is true, which is LF flag 1 is 0 and flag 2 is 0. In this case, we want to have some meaningful value for average. Uh, let's call it average default. Okay, this is just, we have no information available, but we still want to tell it something, otherwise the control system will freak out. So we'll define in the bit. Let's call diff equals 0, and I'll call the average default. I'll define it in the init. So we can put here call that. So I would say 0.15 is a good estimate of it. So let's put that. Uh, reprogram the motors to go at speed of 1 and move this robot down and then watch it move and see what it records the value. Stop. It's a 0.14, diff is 0.016. Keep running. So you can see the distance is increasing as expected, and this is almost the same. Okay, so this works, and this shows how to read the proximity sensors.